Hello everyone, my name is Andreas, and today I want to talk to you about constraints that arise in neural network output layers. This is joint work with my supervisors Antonio and Adam. My goal in this talk will be to raise awareness about constraints that arise when we have linear output layers that have many more outputs than inputs. Specifically, I will focus on multi-label classification, where such an output layer is called a sigmoid bottleneck. Would you be surprised if I told you that we can prove that such output layers have a very large number of outputs that can never be predicted? If so, stay tuned, and in the next part of this talk I'll explain how this happens, and I will then show that this does not necessarily have to be the case, and I will show how we can reparameterize this output layer such that it does not have this limitation. We will focus on multi-label classification datasets that have a large number of output labels. One such example is the Mimic dataset. Here, we're given a clinical document, and we're asked to assign it a set of findings, where each finding is a label. So for example, this document may have these three labels assigned to it, and the remaining findings from the label vocabulary may be absent. We call every finding that is present an active label and represented with a plus, and every finding that's not present inactive and represented with a minus. So overall, this way, every output of a multi-label classification problem is this combination of labels seen here, which is a label assignment, and we represent with Y. It is precisely these complete label assignments, a subset of them actually, that will not be possible to predict for any input for the model we will look at. Okay, so what output layer would you use to model the Mimic dataset? I think you'll agree that the easiest and most common solution would be to use a linear sigmoid output layer. This is in fact the default implementation in many frameworks and is a very common baseline in papers. To implement such a layer, we take a feature encoder that could be as complex as we like, and we append a linear layer W after it. This linear layer has one output per label. In addition to the Mimic dataset, we'll also see two other datasets, the BioAsk dataset and the Open Images dataset, which also have a very large number of output labels. Implementations of the sigmoid layer for these models tend to have a very low dimensional feature vector, which makes this W low rank. Now under such scenario, we have what is called a Bottleneck sigmoid layer, or BSL for short, and it's precisely in this circumstances where we get outputs that are impossible to predict. Okay, so let's apply the BSL to the Mimic dataset. So if we open the classifier, we have our feature encoder, we have an input, which is a document, we get a feature vector, and now we want to predict labels. The way the BSL does this is we compute a dot product per label, so we have a weight vector per label, and these are the parameterization of the BSL, so each row here is one of these WI vectors. And we compute the activations for the labels in the Mimic dataset by taking the sigmoid of each of these dot product activations. So these are the probabilities for one input, and maybe this is the probability for another input. And importantly, when we make decisions about which label assignment to have for this input, we usually threshold at 0.5 probability. If we use this common decision rule for making predictions using a BSL, it turns out that there are outputs that can never be predicted. To see this, making predictions by thresholding probabilities at 0.5 is equivalent to taking just the sign of the activations of this linear layer. See our paper for more details. We say that an output label assignment Y is Argmaxable if there exists a feature vector X such that if we take the sign of the activation, we get Y. As alluded to earlier, BSLs always have Argmaxable outputs. To see how this arises, let's take the case of a two-dimensional feature space, the plane here, you can imagine, and let's start placing classifiers in this space, where each line here is the decision boundary. So we define where in feature space this label is positive and where it's negative. So for this classifier, the first label is positive if we fall in this region, and it's negative here. Now notice we don't have a bias vector, so all lines which are the decision boundaries will pass through a single point. So here we have a second label, and now we can still predict all possible label assignments with this configuration. However, notice that if we add a third classifier, then because we pass through this point, we are forced to only be able to represent 6 out of 8 possible label assignments. Namely, in this case, for this W, plus minus plus and minus plus minus can never be predicted no matter where we are in feature space. So these label assignments are unargmaxable. While this was just a 2D example, if the gap between N and D is greater, then the problem is even worse. To see this, we consider having 1,000 labels and shrinking dimensionality D while looking at what percentage of the label assignments is still argmaxable. We quickly see that shrinking even to 250, we're left with only a tiny budget of argmaxable label assignments. And this trend continues further. However, maybe this budget of argmaxable label assignments is enough to actually cover all the label assignments we have in our training data and our test data. Because the label assignments in general are sparse for the datasets we're looking at. So K here is the number of active labels per label assignment, and we see that for all these datasets we're looking at, the number of active label assignments is bounded above by either 80 or 50. However, it turns out that this theoretical problem does indeed turn up in practice as well. To see this, we fit models with a BSL output layer to all these 3 datasets. See our paper for more details on how we do that. And it turns out that there are indeed unargmaxable test set labels. So there are meaningful test label assignments that can never be predicted in all of these 3 datasets when the sigmoid bottleneck is narrow enough. So when D is close to 100. Okay, so we've explained what a bottleneck sigmoid layer is and highlighted its weakness, namely that it can have meaningful label assignments that can never be predicted. Wouldn't it be nice if instead we could actually create an output layer that has all sparse label assignments that we know are needed for the task at hand be argmaxable by construction? We show that this is actually possible, and I will elaborate on how next. The nice thing about this output layer, which we call a DFT layer, is that it retains the simplicity of a BSL, but also provides us with the argmaxability guarantees we like. Recall that all 3 datasets we fit our models on have label assignments that are sparse. More specifically, all label assignments have an upper bound on the number of active labels, K. What does this have to do with the guarantees we want? Well, it turns out that there is a beautiful geometric result we can use. That is, there is a family of matrices with 2k plus 1 columns that give us the guarantees we seek. Moreover, these matrices are defined by a remarkably simple property. I do not have time to go into the details about this property that is stated here as an informal theorem. You can see our paper for more details. However, it involves the determinants of submatrices of W, and it's a very simple check on these determinants. What I can do and want to do here is I want to give you visual evidence that the guarantees are true. While I cannot show you this visualization in higher dimensions where it is arguably more interesting, here are the decision boundaries for such a W with 6 labels in 3 dimensions. So in this case we have k equals 1. Now for k equals 1, it is clear that all 1 active labels should be argmaxable, and indeed if we look here around the 0 active label assignment in the middle, we see that the 1 active label assignments are indeed argmaxable. Okay, so what's another beautiful fact is that the discrete Fourier transform matrix does actually belong to this family. This is great because we get efficient matrix multiplication if we fix W to be this matrix. We have a fixed matrix, so we have less trainable parameters. And because we know the matrix, we can actually change the layer before this output layer in a way that we can speed up training. Check the paper for more details on how we do this. However, since W is fixed, it turns out that we do actually need some trainable parameters in the output layer. And what we do is we concatenate D trainable columns, so namely the size of W in the BSL, onto this fixed matrix, which gives us a comparison that has a very, very similar number of training parameters. So namely what we do is a BSL has this W matrix that is all learnable. We replace this with WDFT that has the first 2k plus 1 columns fixed, and then we append the learnable columns onto W. And we then fit these two models, the BSL and the DFT layer, the BSL and the DFT, to the tasks at hand. Now, if we do that, the results, recall from earlier that the BSL has a large number of test set assignments that are unargmaxable when D is small. The DFT layer doesn't have this limitation. As maybe is expected in theory, we also verified this in practice. And then, in addition, we also evaluate the DFT layer on metrics. So we look at F1 at 10 here and compare it to the BSL. And here D is the number of trainable dimensions. And on the right we can see the number of trainable parameters, which is very similar in this case for the two models. As can be seen, if we have D equals 100, we can outperform the BSL for D equals 200. And this means that we can actually replace a BSL that has more trainable parameters with one that has fewer trainable parameters. And moreover, due to the initialization trick I mentioned earlier, the DFT converges faster. So here we can see how training loss changes as we train the model for longer. And if I translate this into training time, we can get a speed up of up to maybe 2 hours in training. Similar results are also true for the other datasets, but see the paper for more details. To summarize, we have analyzed a commonly used model for multi-label classification, namely the Bottleneck Sigmoid layer, and have shown that when we use such an output layer, there must be output label assignments that can never be predicted. Moreover, if we use such a model to fit a specific dataset, when the bottleneck is narrow enough, there are even test set label assignments that can never be predicted. However, the latter need not be the case. We showed that if we fit our proposed DFT layer to such a dataset, we can actually guarantee that the sparse label assignments are argmaxable by construction. In such a sense, we say that we have tamed the Sigmoid bottleneck. Furthermore, the DFT output layer can be more parameter efficient and also converges faster during training due to the initialization trick we mentioned. If you have any questions or would like to discuss something in more detail, I would be delighted to have a chat in Vancouver.